Hello and welcome into today's webinar from WorldCast Systems. My name is Kevin Campbell. I'm the Sales Director for the APT brand of codecs within WorldCast Systems, and I'll be joined later in this webinar by my colleague Hartmut Forrester, who's the Product Manager for our APT codec range here at WorldCast Systems. So today we're going to talk about next generation broadcast chain and what that involves in terms of codecs and codec technology. So we have four main building blocks that we see as constituting the next generation broadcast chain. That would be composite MPX, which is the AS192 standard, but also the analog composite or MPX distribution that's been around for a number of years. So that would be the first building block. Second building block we see is the compressed MPX that we've developed, and this is a new development, a new algorithm from APT, and this solves really the problem of having the higher IP bandwidth requirements associated with composite or MPX. Third point we'll talk about is SynchroStream, and SynchroStream, again, it's a technology that APT have developed in-house. It's an algorithm that we use to distribute, well, up until this point, largely baseband audio signals between studios and from studios to transmitter sites using our dual redundant streaming technology. Fourth building block to the next generation chain is another new development from APT, which is our SynchroStream technology. So we've had for a number of years time alignment based on NTP, and now we have a time alignment based on SFN and a GPS 10 megahertz 1 PPS input on the codec. So my colleague Hartmut will talk in a little bit of detail about this development, which we're very excited about. So first of all, let's talk a little bit about composite MPX. So conventional distribution, we've had MPX for a number of years. A lot of the 950 systems in the US, for example, would have distributed composite MPX in the analog format. In recent years, the standard, the MPX AS192 standard, has been developed. And that allows for digital MPX transmission. So an AES cable can take the full processed stereo signal and distribute that across typically an IP architecture. So what that has allowed is for FM broadcasters, and we talk about FM radio and signal distribution here, it's allowed the FM broadcaster to realign his broadcast chain and move the processing to the central studio and distribute the stereo encoded signal from the central studio to his main transmitter sites. So you have your sound processor, which can be any sound processor with an AS192 output, which the newer range of tier 1 audio processors would support. You take that AS192 signal and plug that directly into your codec. So APT, of course, is offering this I/O or interface onto their codecs, but of course some other vendors are as well. And then we distribute that signal across the microwave IP link, managed IP link, and even the public internet, which we'll talk about in the context of SynchroStream. So this allows you to have a lot less audio processing hardware in your chain if you can have that centrally located at the studio. It also allows you to distribute absolutely your sonic signature. So each signal turning up at the transmitter side is an exact replica. You're not using a mixture of different processors, a mixture of different profiles on the processor. So we can also do a hybrid of analog or digital composite MPX, which is very popular because we have, in some instances, a newer processor at the studio side. And this is typically, it's not always the case, but typically we have a newer audio processor at the studio side has the AS192 composite MPX input, and then at the transmitter side we could have some of the newer transmitters, and of course I'll mention Creso, which is the AS192 input, but we could also have then a mixture of older legacy transmitters which only have the composite MPX input. So we can mix and match here with an ingestion on digital AS192 composite MPX, and then an egress on the codecs at the far side and into the transmitter on either digital composite MPX or analog composite MPX. So it's a hybrid. So with the AS interfaces, a single SEBU cable can carry the entire encoded signal, which is coming from your audio processor. That gives you the potential to eliminate any analog interferences which are within the chain. It also allows you to have very sensitive level adjustments, as everything is digital from end to end. And you've got the ability to operate a fully synchronized FM transmitter network, which my colleague will talk about in the context of our new SynchroStream technology. But essentially, you have now a complete digital end-to-end transmission path if you have the newer transmitter at your transmitter sites with the AS192 input. There's no analog at all. So with composite MPX, one of the drawbacks is the overhead in terms of IP bandwidth. You need more data because you're doing the entire encoding of the stereo signal. So we have a couple of, well, 3 or 4 different profiles in our codecs, which will allow you to do the full 24-bit MPX composite, which is taking 4.6 megabits, and we can do a 16-bit, which again on the full spectrum is taking up to just over 3 megabits. But then we also do a bandwidth limited version, which will allow you to do the 16-bit at around 2 megabits. So this actually chops the signal right after the RDS carrier, where the signal from 64 kilohertz up is ignored, because in those subbands, largely in most regions of the world, there's no information contained. So we can safely chop the signal just after the RDS at 64 kilobits, thereby reducing the bandwidth and allowing a transmission path of 2 megabits. So one of the problems with any packetized network, and this is true of MPX composite as it is with IP audio, we have to get the signal there in real time. We can't use any sort of TCP/IP or resends on that IP network. So we always have to use the RTP/UDP protocol. If we lose packets, the packets are not replaced if it's a single RTP/UDP stream. And with composite MPX, we have some really nasty artifacts if we lose packets on that MPX encoded stream between the studio and the transmitter site. So those drop packets manifest themselves in overshoots, which in many territories of the world will be punished quite severely by the regulator, as you'll be over-modulating against the permissible 75K signal. So there's a couple of ways to mitigate against IP packets being lost. You can, of course, use a managed IP link, which is expensive and sometimes not always available to very remote transmitter sites, or you can eliminate them, any lost packets on the stream, by using a technology like the SureStream technology, which we offer in our APT codecs. However, for many transmissions, SureStream protection is not available or is not used. So we still need something to absolutely eliminate any chance of overmodulation on a signal which is affected by drop packets. And we have what we call our overmodulation cancellation algorithm, which is absolutely inherent in all of our MPX over IP coding schemes. So in every MPX over IP variant that we offer on every codec, we include the overmodulation cancellation algorithm. So just a few little snapshots of the effects of the overmodulation. So you can see the correct deviation with overmodulation cancellation, 2% packet loss. This is just some statistical modeling, and 2% packet loss is quite high, but you can see that it can cause these overshoots with the red part of the third diagram. They're showing you the level of the overshoot. So the overmodulation cancellation algorithm will absolutely stop that overmodulation or chop that overmodulation using a filter, and that's really an insurance against any drop packets and the cancellation of that unwanted artifact, which can bring you trouble with the regulator, depending on which country of the world you're operating in. So a new technology from APT is the APTmpX. And basically what the APTmpX is about is saving the bandwidth associated with transporting composite MPX. As I say, we had four different flavors on the original linear MPX composite, which ran from 4.6 megabits to 24-bit non-bandwidth limited version, right down to about 2 megabits for the bandwidth limited 16-bit version. However, that's still slightly high if we consider that typically broadcasters are transporting FM quality baseband audio with 15 kilohertz resolution at around 256 kilobits, 320 kilobits if you add the packetization. So what broadcasters have been asking us for is a bandwidth reduced, further reduced implementation of composite MPX, and we've come up with this new algorithm, which is the APTmpX algorithm. So this further reduces the bandwidth from 2 megabits or just over 2 megabits down to 864 kilobits, with the bandwidth limited to the 64 kilohertz frequency. Again, in most, the vast majority of the countries in the world, there's nothing carried above that 64 kilohertz into the 88 kilohertz range. So APTmpX is now included, brand new feature on all APT codecs with the MPX license invoked, and that's included at no extra charge. So that's a non-destructive compression for MPX composite, which will get you a payload well under 1 megabits. So that really brings into play more the SynchroStream technology, which has been used for many years to protect baseband audio signals, for audio distribution, and also for STL. Now with this lower bit rate, we can start to think about protecting also the MPX composite. So you use two divergent links, and the theory is that if you lose packets on one link, those packets will be returned on the second link. So our real-time advanced resequencer on the decode side will patch everything back together. Of course, you still have also the OMC algorithm, which is also an integral part of the APTmpX, as it is with the other MPX profiles within our codec, and that OMC algorithm is the overmodulation cancellation. So it's really a belt and braces approach. The best, of course, is that you protect with SynchroStream and make sure the composite signal is absolutely 100% intact. However, if you do happen to lose a packet on the way, you still have this protection from the overmodulation with the OMC algorithm. So just a quick slide about the composite MPX and the non-destructive versus destructive compression or approach to composite MPX. So there are some competing technologies on the market that take a completely different approach. So what we're doing here is a non-destructive reduction in the data rate. So we're not disassembling the signal that's generated at the central site. So you could have your big processor, your tier 1 processor, $15,000 processor sitting at the central site, creating your sonic signature, and then you want to distribute that across the IP network to your transmitter sites. So with the APTmpX approach, we will not pull the signal apart and reassemble it at the far side. For us, that's against the ethos of what the broadcaster is trying to achieve by rearranging his broadcast chain in the first place. With the competing technologies, what is happening is an absolute reconstruction of the signal. So it's disassembled, and then the audio is reduced quite drastically with psychoacoustic algorithm, and then the stereo image, the composite signal, is recreated at the far side. So with our approach, you will have a more faithful representation of the original signal. With the other approach, okay, it may have a slightly higher compression rate, but the penalty is absolutely that the signal will differ quite substantially from the originating signal generated at the studio site. So we're doing a gentler compression. The data rate is not as high in terms of, or sorry, the data rate is higher, but the compression is much gentler. But you're still getting less than 1 megabits in the payload, which for IP links, even to some remote transmitter sites, is well usable, even over public internet. So just to sum up on those slides regarding composite MPX, so the reason or the rationale to do it, to change the composite MPX from baseband audio, is to drastically reduce the amount of hardware. So as one big processor at the studio will now be able to be used rather than 10 or 12 processors at the 10 or 12 transmitter sites that you have. So it's a big reduction in audio processor spend. You can keep control of your sonic signature by eliminating the number of devices. So one device, and then the final limit or clipping is done on the soft processor within the transmitter itself, which is in many transmitters. It's in our Cresso brand, for example. You have the flexibility still to have a hybrid architecture where you want to have a digital composite at the studio side, digital composite at some of the transmitter sites with newer transmitters with the AS192 MPX composite input, and then you have some older transmitters. You can still feed them analog composite, even if the studio signal has been generated in digital composite. We can bend it across to analog, no problem. You've got now, with the latest development of the APTmpX, you've got more flexibility in terms of the bandwidth. So we've got the full 24-bit linear composite at 4.6 megabits, right down to the APTmpX composite MPX, which is in around 860 kilobits. Packet loss is covered, so we've got SynchroStream to help with that, and that fits very well with the less bandwidth that we now have on APTmpX. So public internet delivery for MPX is becoming more of a reality, and we also have the overmodulation cancellation as well, just in case some packets do sneak through. Some lost packets do sneak through. So you're covered with SynchroStream. Don't have SynchroStream, you still have the overmodulation cancellation algorithm. So I'm going to hand over now to my colleague, Hartmut Forrester, and Hartmut's going to talk a little bit about another new development from APT, which is our SynchroStream for FM SFN networks. Hartmut, are you there?
Yeah, I'm here. Thank you very much, Kevin. So,
okay, Hartmut.
So you can hear me very well, yes? Can you?
I can indeed.
Super.
Go ahead.
So I thank you for the very sophisticated introduction about the importance of consistent signal chain, centrally generated from a sound processor and then transmitted over the network as a composite MPX signal. So the two topics relate to each other. So now we are going to talk about the SynchroStream. So this means synchronizing transmitted content in the time domain. So we have developed and implemented a new feature. Hold on. So we are able to synchronize different streams or different destinations on the time domain very perfectly. So SynchroStream is the new implementation for perfectly synchronizing the audio stream, and perfectly means, you know, we are in a domain of the speed of light, because in the context of single frequency networks, we will talk about this in the coming slides. It's very important to understand why this high precision is so important. Therefore, SynchroStream is a hardware and a software implementation in the latest APT IP codec generation, and we are using external clock references from the satellite, from the GPS signal, which is the normal standard 10 megahertz clock, and the 1 PPS clock for time definition and time point definition. So the special performance of SynchroStream is, and we are very proud about this, is the high stability. It keeps your synchronization in a very, very tight time, and also the finest adjustment of the synchronization of the increments. You know, you can trim your synchronization in the time domain. So we have two approaches, or two topics, or two tools to synchronize over IP. First is the compensation of the dynamic latencies in the IP network. So IP networks are okay, up to a certain extent stable, but jitter and timing influences, you know, are very common. So you cannot compare it with a synchronized link. So we have dynamic latencies to compensate, and that we can do up to 1 second in the 10 megahertz clock domain. And if we apply the NTP time base as well, and in addition, we can do it up to 5 seconds. And therefore, we need the 1 PPS signal as well. And then after we have compensated, or we have defined a latency, a fixed latency over the IP network, we can also add fixed delay lines into a single line between two transmitters, for example, in increments of 125 nanoseconds, which is a novelty at all. So this is an eighth of a microsecond. So we are very precise, because we are talking in the domain of speed of light in the carrier propagation time. So it's a hardware and a software implementation. It's a hardware and a software implementation. So the hardware, and this is the reason why we need the latest IP codec, APT IP codec generation. It's a hardware add-on we have to provide here for the input of the 10 megahertz clock and the 1 PPS signal. So therefore, the next generation, or the current generation, it's revision 3 of the IP codec, provides this as an option. So you can order this on build time. It's also possible to retrofit it, but you know, the precondition is, you know, it has to be the latest version of IP codec hardware. The second is the software, and software I will show you. Where is it? It is not really huge on the GUI. So the presentation, or the representation of the time adjustment or time delay is simply in a single stream configuration. This is the screenshot from a decoder. So for example, you can see here the link latency trim value is in milliseconds, so you can adjust the trim value from a given target latency, which is applied in the encoder, and also the fine trim, which goes into sub-microseconds. So this means in nanosecond area, in the increments of 125 nanoseconds. So you see on the middle and the right, I point with my mouse to it, 125 nanoseconds adjustment here, and you can also go to half of a microsecond, and also further in increments of 125 nanoseconds. So this is your decoder adjustment for the fixed delay lines to adjust time differences between two transmitter sites. Right. The perfect application, and you have seen it before, is of course a single frequency network for FM applications. So we need this position timing for single frequency networks where each transmitter in a group transmits in the same carrier frequency. As a comparison, on the left-hand side, you see the multi-frequency network application, which is common for APT codecs in the while. And for this, we only need time alignment in the domains of milliseconds, because we are not synchronizing technically the carriers here. We only synchronize the demodulation of the audio. So the carrier will not interfere because they are in two different frequencies, but the content should not jump or should not have a lag, between moving from one coverage area into the other coverage area when the receiver changes the frequency controlled by the RDS. So the modulation, the demodulated signal should be in the same time. Therefore, and the instance we measure this is the human ear. So we are adjusting in the domain of milliseconds. It's a completely different thing on synchronized carriers, which is on the single frequency network. On the single frequency network, we are synchronizing the modulation of the FM carrier in the domain of the speed of light. So we have to be much more precise in our increments of adjustment. And this is the topic or the context we are describing, or we're discussing SynchroStream. Right. Question is, why is a synchronized network desirable? So it is of course not the solution for all broadcasters, not the solution for all territories or terrains, but it's more and more a common application. And it consists of 2 or more transmitters broadcasting on the same carrier frequency, and to create a larger coverage area with smaller transmitters, with more than one smaller transmitters. And the reason for that is, of course, to reach more listeners, which would not be reachable by terrain shadows, or to allow listeners not to change the tuning on a long time. For example, on driving on a highway, there's the best European example for this is the highway radio 107.7 megahertz in France, where you just tune this 107.7, and you're done from the north to the south. And of course, it has also commercial and economical reasons for it. Available RF spectrum is rare, and the frequencies are very valuable. So if you can use your frequency multiple times for increasing your coverage area, it's very desirable. And the other point, or the other reason for that, could be that a large transmitter on a high mountain location, on a high mountain top, can be much more expensive to operate than several smaller transmitters. The arguments or the reasons for this is the energy consumption. Of course, we have very energy efficient transmitters nowadays, but cooling, heat dissipation is a problem. The infrastructure as a common topic, we have to bring all the links and lines is the high power to a high mountaintop, and then seasonal accessibilities. In winter time, it's very difficult to reach transmitter sites, or many transmitter sites are not reachable in winter time because of snow and weather conditions. And there are also other reasons from broadcasters. Right. How to achieve the goal of an SFN? What is the goal? The goal is to reduce interference and overlap zone and to manipulate the geographical location of these interference or overlap zones. And this webinar is not talking about how to set up an SFN. It's just to explain how SynchroStream can help you to optimize your SFN. First of all, you have to specify the location of your transmitter, mountain top, valley, distance between each transmitters. Then also the definition of the different power levels between the transmitters, which is very, very important to adjust your overlap zone by manipulating the power of each of the transmitters. So you can have one transmitter with a very high power emission and others with a lower, or the combination of both of three in a three-party organization. Then, of course, you have to consider the topographical conditions, shadows from mountains, buildings, other terrain instances. To reduce all these artifacts, on the RF and the RF domain. Of course, antenna characteristics, how your antenna is designed to have an omni emission or a pointed emission, and the positioning on the tower and the height. And then, of course, and this is the link to the topic Kevin was talking about earlier, you have to have a very precise MPX signal level on all the transmitters. It has to be the same. It's very important for your good reception in the overlap zones. And then at the end, for the resulting overlap areas, you need to synchronize your modulation to have a very good tool to precisely define where your reception is the best, where your overlapping zoning sounds the best with less disruptions. Two things to consider. First of all, we need to synchronize our carriers to the same carrier frequency. So all the transmitters in an SFN group have to transmit on the same carrier frequency, and this carrier frequency has to be locked by an external clock. So we use usually the GPS as a reference clock, which is only the 10 megahertz carrier, the 10 megahertz to synchronize the carrier. And the phase and the phase is not really important. You need a frequency locked condition. So when the entire network drifts because of the GPS drift, then all transmitters drift synchronous, in the same direction. So it stays as a single, or it appears as a single RF coverage. So this is done by applying the GPS 10 megahertz clock directly to the transmitter. That's all you need for your transmitters. So the importance of equal content level. So the content level is your MPX signal or your audio signal. And here, the method of transmitting MPX through the network is the best method to do it, because you can control your MPX level centrally on your processor. You have a digital chain. The signal is transmitted in the digital domain, and the level is safe. So this is just a digital value over the entire chain. There's no analog interference or any influence on this signal. So because a level difference between the transmitters is at least in the same way important, or has the same negative effects, at least the same negative effects as having a misaligned timing. So for example, 0.1 dB is already considerable recognizable. So you have noises and your noise level raises, and your audio can be distorted by having this different content level, because you're applying a frequency modulation to the carrier. And if, for example, if you modulate the same tone, imagine a single tone with 10 dB as an example, or full level, the maximum level, it equals a frequency deviation. if you do the same tone on a lower level, it equals also a frequency deviation, but a different. So if you have an overlay between these two different modulation frequencies, you have mixed products. So you have additional frequencies, or you have artifacts on subtractions. So the MPX level defines the quality of your demodulated audio in the FM receiver. Therefore, the 100% digital chain, as explained earlier, is the most desirable and recommendable way to transmit content for SFN. By the way, the APT AOIP module can adjust the analog composite signal as well, very precise in increments of 0.025 dBu. So you have also here a very, very precise level adjustment to optimize your level on your analog or in your hybrid signal chain. So need for equal content level. Here's another repetition of how it can be done. So you see on the left-hand side of this application, the IP decoder fed by the GPS signal for synchronizing the content, the modulation, and there's a single AES cable between the decoder and the transmitter to carry the MPX signal, which is a digital MPX. So this is the best way. There's no analog influences and interferences possible. Right. So in an interference zone, which is the overlap area of the remaining transmitter adjustments on the RF carrier, you have an overlap area, which is the goal to avoid it or to minimize it. But in practice, you have an overlap area, and in this area, the receiver or the FM receiver in your car, in your house, or whatever you have must get the RF signals from both transmitters simultaneously, like in a multipass situation. So you should receive at the exact same modulation at the exact same time. So exact same modulation means on the exact same MPX level, and the exact time means on a precisely adjusted delay line. So RF again propagates in the speed of light, so we need increments to shift the modulation in the domain of the speed of light, which is microsecond or sub-microseconds. So we are insisting in having sub-microseconds because the speed of light, for example, a change by 1 microsecond means already a propagation difference in the terrain by 300 meters. So in 1 microsecond time, the modulation travels 300 meters. So if your system keeps your delay stable within a microsecond, which is much in my opinion, then your zero delay zone, where you have matched your timing exactly, swings within 300 meters, which is large. And if the smallest increment of the delay adjustment is also microsecond or 2 microseconds, then you can move your zero delay line only in 300 meter steps, which is also a big difference, a big distance. Sometimes it's desirable to move it far away from an area, but to have modulation precisely adjusted in the overlap area to optimize the receiver quality, you need less than 1 microseconds, and that's the reason why SynchroStream has the sub-microsecond increments. So let me explain this on this image here. So it shows you on the left-hand side a transmitter which is called the main transmitter, and this is an application where you have a large transmitter on a mountaintop, and you have a booster or a gap filler to cover a shadow zone with a lower RF power. So this lines, you see this bows here. This represents the modulation traveling from one transmitter and the modulation traveling from the other transmitters, from the left to a point and from the right to a point. So it's not the RF as such, it's the modulated RF. So it's the in speed of light. So you see 1 microsecond equals about 300 meters. And the goal is to have an equal delay line adjustable where you like to have this. So if this is, for example, then a populated area, a city, or it's a street, or it's the highway, you want to optimize the reception in this line or area. It's never, in practice, it's never a line, it's always an area. So this delay line or this zero delay line or equal delay line is defined by the timing from the propagation of this modulation and from this modulation. So we have two different distances. As an example, 1.2 kilometers and here less than a kilometer, and you see the timing is very different. So without having a time adjustment here, so we need 4.125 microseconds to reach this point. And from this side, we need less. So we have to add a delay to exactly reach the overlapping point at this red line. Therefore, 125 nanoseconds equals 37 meters. SynchroStream provides this, and we say it's the most precise tool in the market at the moment to adjust this zero delay line as precise as possible. So in a practical or another example application, first we have to do we have two steps to set up the timing correctly. First of all, we have to compensate and to manipulate we have to compensate the STL dynamic delay, which is done by setting the target delay in the encoder. In this example, we are using 150 milliseconds. It's only an example to have a number here. So we set in the encoder 150 milliseconds as a target delay that the packet which has this timestamp reaches or is played out at the decoder 150 milliseconds later. So each STL, depending on the length and on the quality of the link, or the capacity of the link, has different delays. So for TX1, for example, we have said it's 24.3 milliseconds. For the STL2, we have said it's 51.1. So it's more or less twice the delay. And SynchroStream now calculates the target delay read from the packet timestamp and the time which has been passed already after it was sent, and calculates the remaining difference from 125.7 milliseconds to achieve 150 milliseconds as a target delay to have the audio exactly here at the antenna. And the same is on the TX2, which has a different link delay, which is 51 milliseconds, and so therefore we have to add another 98.990025 milliseconds to this delay line or to this link to have exactly the same timing with the target delay of 150 milliseconds calculated over different latencies on the network. And this delay is never stable. So we have jitter, we have perhaps delay variations here, but SynchroStream compensates dynamically. So now we have synchronization on the transmitter antenna, but we want to have synchronization in the field, in the terrain, on a different position. So the goal here is, this example shows, how to move the zero delay line. So this means the line in the overlapping zone where the reception should be best, 70 meters closer to TX2. Therefore, we have to add now fixed delays. So for the fine trim on TX2, so on TX1, we don't do anything. It's just this delay here. On the fine trim on TX2, we add 250 nanoseconds to move it 70 meters. So I explained this on a step-by-step instruction at a little bit more structured here. So first of all, we have to compensate or to define the variable latency of the STL. to compensate, which is done by the target delay setting in the encoder. So you do it in your studio on your encoder near to your equipment, say, okay, 150 or 100 milliseconds or 50 milliseconds, whatever it will be, whereby the highest SDA latency, of course, determines the minimum latency from the value of both transmitter sides. So it cannot be shorter than the longest line. So the longest line is 50, then it has to be 100 or 80 or something like this to have a little bit of buffer. So in this example, we have 51 on SDL2. So on the encoder, the example target delay is set to 150 milliseconds, and then SynchroStream calculates the value of the buffer for each of the locations to reach 150 milliseconds. So synchronization of modulation at the antenna. So now we have to move the modulation between the two transmitters 70 meters towards transmitter 2. And therefore, we need to increase our fixed or constant latency on transmitter 2 to allow the modulation from transmitter 1 to travel 70 more meters towards transmitter 2 before the modulation hits each other. And this is the way, you know, how it is done. So again, to this slide here, synchronization of modulation at the antenna by setting the target delay, and then calculating the delay line in this example towards transmitter 2 by adding extra delay in this little increments of nanoseconds. Right. So that's the end of SynchroStream. So we are happy to answer questions. Sometimes it was perhaps not so clear for everybody how all this works. So we are happy to receive your emails or your comments. Thank you very much. So I hand over to Kevin.
Thank you for that. Thank you, Hartmut. So very concise and succinct explanation of SynchroStream. Much appreciated. So just to sum up some key takeaways from this presentation, the next generation broadcast chain, and just to understand as well, all of these technologies can stand alone. So MPX composite, if you need to do a single STL link with MPX composite, that's entirely possible. The idea of this presentation was to outline how we can use all of these technologies to create the next generation, but they're all absolutely applicable as standalone technologies in their own right. So MPX composite, it's something we've implemented on the codec for the last number of years. We are going from linear 24-bit to 16-bit bandwidth, frequency constrained to 64 kilohertz. So that allows you to go between 4.6 megabits and 2 megabits, just over 2 megabits. The new development is the APTmpX. So this allows us to dip down to a bandwidth of around 860 kilobits. And this is the first non-destructive MPX compression technology on the market. So this is a new algorithm developed in-house and implemented on all our codecs where you've switched on or purchased the MPX license on the codec. The over-modulation cancellation algorithm is what we call an insurance policy on any lost packets. But the greatest insurance policy is our SureStream technology. So we use dual links, redundant links to provide multiple copies of the content at the decoder. And this we've had as a licensed feature on our codecs for many years for baseband audio, and now with the new APTmpX compressed, it's more relevant because we're able to have public internet links that can easily handle that payload of 860 kilobits. So SureStream is a very real option now to protect your composite links to your transmitter site. And then finally, Hartmut gave us the very nice detailed presentation on SynchroStream for SFN and FM in particular, we have the finest granularity of tuning there in terms of how we can move that line of delay and the what's commonly known as the mush zone. We can really reduce that mush zone quite dramatically thanks to the accuracy and the implementation on our codec platform of the SynchroStream technology, which again is a new development on the new release of code for both the APT-IP codec and the one you frame with the LIP card. So SynchroStream and APTmpX, the compressed MPX, both new in the new release of firmware. So the benefits to implementing this next generation broadcast chain, well, less complexity, a single audio processor sitting at the studio distributing a uniform sonic signature sound to all your transmitters, and now with the ability to have a digital alignment more accurate than any distribution or codec platform on the market today. So an SFN digital alignment that can't be battered by anyone else. Less cost in terms of the amount of hardware. The obvious example is the processing and the RDS encoders. So we have, instead of processors and RDS encoders sitting at every single transmitter site, we now have one processor and RDS encoder sitting at the central site, and then we can use a software limiter or clipper on the transmitter side. So that's less cost in terms of initial hardware spend, but also in terms of maintenance. And New Zealand is a place where we've seen some SFN and a lot of MPX deployments, and that's for that very reason, where they have high sites that are tough to get to for 6 months of the year, and they want less gear at the site. Means less maintenance, means less potential trips to the site. Quality of the signal is maintained and quite often improved. If you've got that full digital end-to-end signal, you've got no analog of interferences in the high RF fields within the transmitter site. So it's digital right from the audio processor to the input of the transmitter. And you've got all the protection and assurances from the SureStream algorithm in terms of protecting the actual data stream, either audio or MPX composite that you send across the IP links. And then you've got the overmodulation cancellation algorithm as well. So those are the reasons why, and we've given the full suite of tools on our codec range to enable you to take advantage of those benefits. So I just want to wrap it up here. I can see there's some questions coming in on the message board. We will answer those questions in the next day or two. Those will be posted on our website with an archive of this presentation. Thanks for taking the time to listen today. You can also find Hartmut's details and my own on the website if you want to address any questions to us directly. Okay, thank you very much.